So these two last problems on the homework for chapter D for us are meant to sort of take us through a discovery of how we would do Lagrange multiplier type problems for a function of three variables. And so in DF5, it's sort of just getting us used to the idea of when we have a three variable function, it's possible for us to have more than one constraint because each constraint equation for a function of three variables is going to define a surface inside of three-dimensional space. And so if we use two constraints, those constraints can intersect, those two surfaces can intersect along a curve, and we can use that curve as the constraint for our optimization problem in three dimensions. And so this question is about what are we going to need to do differently if we have two constraints instead of just one for a function of three variables. So let me ask first how the challenging part about this problem, I think, was just getting to the discovery part of what relationship ought to exist between the gradient vectors of f, our objective function, and the two constraint functions h1 and h2. So in the beginning, there's the observation that if we just take the old Lagrange multiplier principle that we want the gradients of f and the constraints to be parallel to one another, and we apply that to a two constraint situation, then it turns out that that is a sufficient condition to give us potentially the maximum or minimum, right? That if f is parallel to both the gradient of h1 and also, so if the gradient of f is parallel to both the gradients of h1 and h2, then that means that f will have a zero directional derivative in the direction of both the h functions constraint and also the h2 functions constraint. And so that is a sufficient condition to get us that sort of critical point, constrained critical point. But the rest of these parts are meant to show us that that condition, while sufficient, is not necessary, that we don't have to have that the gradient of f is parallel to the gradients of h1 and h2. We can actually have a weaker condition and still get us criticality. So part B, the point of part B, is that if I have a direction that is tangent to the intersection of both surfaces, so both constraint surfaces h1 and h2, then that must mean that the angle that v makes with the gradients of h1 and h2 is that it needs to be perpendicular to both gradients of h1 and h2 in order to be tangent to the intersection of both surfaces. And so here's where the rubber meets the road, is parts C and D. Because parts C and D, we're trying to discover a relationship among the three gradients, the gradient of f, our objective function, and the gradients of h1 and h2, which are constraint functions, that give us a weaker condition under which we get a constrained critical point. And the key for this is that it needs to be a condition that expresses these two facts in part C. So we sort of just take a step back in part C and just think about vectors in three space. And in part C, so this is the part I kind of want to start by dwelling on, how do we find vectors, a triplet of vectors, three vectors in three space, such that every vector that's perpendicular to two of them is perpendicular also to the third one, but that no pair of vectors in this list is parallel or anti-parallel to one another. So what relationship among three vectors will satisfy this condition? So I saw that the instinct that we have in this problem, that I think is a good instinct if we can harness it in the right way, is to key in on this clause here, perpendicular to both. Anytime we hear perpendicular to both, that should set off a little cue in our brain that what is probably a good idea. Like, what should we investigate? What might have some relevance here? So the cross product of v1 and v2 is a direction that is perpendicular to both v1 and v2. So in particular, what this tells us is that the cross product would be one of these vectors that's perpendicular to both v1 and v2. And so the cross product, we need to be perpendicular to I as well. So maybe I'll kind of write that over here in the margin as a possibly helpful hint, right? Hint. We want v1 cross v2 to be perpendicular to I, the vector 1, 0, 0. Right? It's also worth thinking about what are the vectors that are perpendicular to I. How would we describe, if we have the vector 1, 0, 0, what do I know about the components, let's call them x, y, z, of a vector v which is perpendicular to I? Like, what constraint does that put on the components x, y, and z?
Well, if x is 0, any vector v would be
Yeah,
perpendicular.
exactly. X is 0, but y and z can be anything. So what we'd be looking for then are two vectors v1 and v2 such that their cross product has a 0 in the x component. Because if the cross product has a 0 in the x component, then that means that it's going to be, the cross product is going to be perpendicular to I. So this is an in particular here. We want v1 cross v2 to be perpendicular to I. And so the cross product needs to have a 0 in the x component. So maybe that will help to get you a little bit closer to what you're looking for in this part C. I'm going to kind of leave that there. We can continue that particular part of the discussion in the Discord if you want to after class, so that we can go to the question you asked about, which is DF7. So in DF7, the condition, the two-constraint, three-variable Lagrange multiplier condition that you ultimately find in question 5 can be reframed in a scalar triple product. So the condition is that the gradient of f dotted with the cross product of the gradients of h1 and h2, when that's equal to 0, then we have a constrained critical point on the intersection of those two constraint surfaces. And so here, we can use this approach, and there's only a part A, by the way. I don't know why that A ended up in there. We can use this approach to optimize, so find the minimum value of the objective function x squared plus y squared plus z squared on the intersection of the cylinders x squared plus z squared equals 1 and y squared plus z squared equals 1. So I think there was a question about this computation in the Discord also, but let me check in with you. Where are you getting stuck on this piece? So I guess I'll say it this way. The tricky part in Lagrange multipliers is almost always the algebra of figuring out how to get your x, y, and z values out at the end of the day. And so in this example, when you take the gradient and you take its triple product with the gradients of the constraints, I think the gradients of the constraints, when you take their cross product, you get something like... what do you end up getting there? I think it's 2... Is it? Let's see. Anyway, maybe I'll skip over this part because I think it was what I saw in the Discord was correct. Is that when you do this triple product, you end up getting something like, was it 8xyz or something like that?
Minus 4yz. That's the first component.
Okay.
And then the second component was negative 4xz.
Negative 4xz.
And the third component was positive 4xy.
Positive 4xy. Okay. Right, so that when you take that, when you do the dot product of those, it ends up being, so negative 8 minus 8 plus 8. Yeah, so it's negative 8xyz, I think, is what you have for that scalar triple product. And so if the Lagrange multiplier condition is that this needs to equal 0, one of the... well, and then you also need to satisfy both constraints, right? X squared plus z squared needs to equal 1. And y squared plus z squared needs to equal 1. And so these end up being your three constraints. And so my what I want to sort of close this example with is that my recommendation whenever we have an equation that looks like this is to use the zero factor property, right? Negative 8xyz equals 0 means that either we must have x equal to 0, or we must have y equal to 0, or we must have z equal to 0. And that gives us three different possibilities for how to then look at the other two constraint equations. So if in the case x equals 0, we can plug a 0 in for x into the other equations and try and solve. In the case where y is equal to 0, we can do similar. In the case where z is equal to 0, we can do similar. And so we might end up with a bunch of different answers here in this case, which is fine. It also is maybe not entirely surprising based again on how the intersection of these two cylinders looks. It looks like it kind of, if x is equal to 0, we're talking about the yz plane. And so this point right here at kind of the top of the intersection of the two cylinders might be one of our potential constrained critical points, right? Same thing with the point at the bottom, which would be 0, 0, -1, and so forth. So it's telling us that when we find our constrained critical points, we're going to be finding them within the coordinate planes, within the xy plane, within the yz plane, and within the xz plane. That's essentially how we can interpret this either x equals 0, y equals 0, or z equals 0 condition. In fact, the equation xyz equals 0 describes the intersection, not the intersection, the union of all three coordinate planes inside of 3 space.